My name is Michael Leamy. I'm at Georgia Tech. I'm going to talk about nonlinear metamaterials, and so I'm going to focus on amplitude dependence that are in these nonlinear metamaterials. That amplitude dependence occurs in dispersion, occurs in group velocity, it occurs in band gaps, and although we heard some metamaterial work, I'll explain exactly what a band gap is. And I'll try to give some information about device implications, how we get tunable devices out of this. So let me give some credit to Raj Narasetti, who was the first PhD student that worked at this. He's now at Gulfstream, also in Georgia. Kevin Mantolo is a student that just finished up. He's now at Sandia National Labs. And then Massimo Rosini's a co-worker, professor in aerospace, and he and I have worked on this together.
And who's the guy on the medal?
Well, he's a guy named George W. Woodruff. So we're the George. See, in the U.S., you sell your name, right? So we sold the School of Mechanical Engineering to essentially his legacy, George W. Woodruff. We lead in capitalism. Okay. So here are the contents. I'm going to motivate the study of nonlinear periodic structures. Why are we interested in this? I'm going to spend a little bit of time detailing a perturbation approach. We're attacking nonlinear difference equations as opposed to ordinary differential equations. We have an infinite number of them. We invoke the Bloch theorem, which allows us to look at a single unit cell. So there's some details in the perturbation approaches we've developed, both Lin step Poincare and multiple scales. Ultimately, they give us a first-order correction to the dispersion. And that leads to everything. Once we know dispersion and how it's corrected in terms of amplitude, then we can do some interesting things with devices. And I'll try to show you some simulations of essentially devices. I'll look at 1D and 2D lattices. Francesco says I work in the discrete world, and I do quite a bit, but this could come from the continuous world where you've done some finite element discretization, and in fact we do that. I'll discuss wave-wave interactions. So much of my talk will talk about one wave, and many devices work on a single frequency, so that's a very appropriate setting to look at. But other devices see many, many waves interacting in some manner, and this gives us the ability to tailor dispersion even further. This is the newest work that we've done. I'll present a nonlinear string experiment. It's our first attempt to really verify and validate what I'm going to show you, and there's much work that's needed, and of course I'll conclude with some final thoughts. All right, so I know we've seen a little bit of metamaterials, but this is a key figure, so I'm going to just step back and try to explain this. This is dispersion, so if you were looking at some homogeneous material, not a waveguide, not necessarily a rod, but if you're looking at bulk waves in a solid, then in this picture what you would see is frequency versus wave number. In this case we call it the wave vector. I'll explain the Greek symbols and whatnot in a moment. But you would see the wave number essentially on this axis and frequency, and most waves are non-dispersive. Okay, you would see a constant phase velocity equal to the group velocity and just be some linear line. Now, guided waves, Lamb modes, and whatnot show non-trivial dispersion, much like what I'm showing. So what I am showing here, I'll wait a second. What I'm showing are typical of metamaterials. So a metamaterial could have an internal oscillator. That would really be your prototypical metamaterial. Even a periodic structure where you have layered media, as long as it's periodically repeating, we can identify a unit cell, and I'll talk just simply about the case where this is let's say a square cell, so I don't have to talk about a reciprocal basis. Then we can follow the unit cell and essentially 1 over the lattice constant. We can follow in this reciprocal space, which is essentially another square. We can follow wave vectors, all right? If we're at the origin, then we have a wave vector of 0 length, and we start at the origin here. As we move across from gamma to x, we'll see a dispersion curve, okay, which is an acoustic curve. We can then go up to m, and so we'll be at our full wavelength in the x, and then we'll have a wave number increasing in the y. And we can actually come down this diagonal. Typically, this curve happens to show us going from m to y and then y back down, okay? So here we are in wave vector space. All of these branches are dispersion branches where waves can be supported. Some of them have negative group velocity. That leads to negative indices of refraction. But most importantly for us is this concept of a band gap. So here you can see a frequency band gap. Here's where we have no dispersion curves. All right, and that really is the promise, much of the promise of metamaterials. What does that mean? Well, that means that if we take this material now and we impose a wave, maybe we use it as a waveguide in some way. If we impose a wave, it's just simply going to bounce back at us. It's going to be an acoustic mirror. Okay, so that's of interest. In fact, we've been using that to concentrate energy and then harvest it. But maybe more importantly, we can cut through the material and make a waveguide. And that's done, for example, or can be done in your cell phone. Your cell phone actually filters with a surface acoustic wave device. Many of them are now phononically enhanced, all right, to get rid of some frequencies that otherwise would pass through. So this bandgap's critically important. We can put a defect in, and then we can have a very high Q resonator in the structure. You can use RF applications where you're using piezoelectric materials and mixing this band gap to do filtering of electromagnetic waves. All right, so there seems to be a lot of promise with these metamaterials. Now, what we're interested in is how do nonlinearities change this picture, and maybe more importantly, how do they shift the band gap with amplitude? All right, that's our exact motivation. We're also motivated a little bit by group velocities and how to exploit that. All right, so nonlinear periodic structures exhibit additional unique wave vectors, wave properties. Here are some that I will not talk about, but just give credit to others. Vakakis, Kyria Dario is now at ETH, she was at Caltech. There's highly stable and localized solutions even when you do not have defects. Of course, there's solitons and other types of solitary waves, breather waves. And then our interest is there's variations in the wave speeds and the propagation directions with amplitude. We see that as an ability to tune. We can put a gain in front of the wave, we can amplify it, or we can dissipate it some, and we can change how it's directed, how the energy flows through the system. All right, so that's what I'm saying here. Basically tunable phononic devices, isolators, filters, logic ports, resonators, etc. And our focus is really on the discrete. This is where I can't really argue with Francesco. We like to work with either systems that are discrete, and phononic crystals can very much be discrete, especially at the MEMS level. You can have stiffness-like elements, you can have mass-like elements. But we work with a discrete system, and therefore we don't have to invoke a long wavelength approximation. All right? That's typically what's done with an equivalent continuous system, to go into continuum mechanics, maybe work with a KdV or Berger's equation. So I'm going to go over this. Maybe I won't say much at length to save a little bit of time. Essentially, the perturbation approach I'm going to talk about is like Lindstedt Poincaré in spirit, although we've been working more with multiple scales now. Multiple scales allows us to do many more things than a Lindstedt Poincaré approach. Okay, so here's what we're working with. This would be our lattice that we're interested in. I happen to show a little more complex case where the lattice vectors are not orthogonal. Each one of these cells repeats or tiles. So you can label lattice vectors A1 and A2. And then you have the reciprocal basis B1 and B2 where we have orthogonality between these. B1 is orthogonal. B1 and, well, AI is orthogonal to BJ where I and J are not equal. We can locate any unit cell, so we can have an integer that says where some translates away from a reference unit cell, and we use the vector R to denote that. All right, essentially, those are the two spaces we work with. Now, the promise with this periodicity is we can reduce everything down to a single unit cell. Let's say we're going to work with the center unit cell. And when we work with linear systems, you can do just that, in fact. You don't have to include all the neighbor cells. Here, we have to include them because we have nonlinear interactions, and therefore the classic block theorem doesn't hold in the nonlinear setting. So we're forced to work with the cells surrounding our reference unit cell. We're then forced to do something asymptotically so we can get rid of all these other cells, at least at the zeroth order, and then find our correction. All right, so I'll explain this process a little bit, maybe in some detail. Sometimes I feel guilty going through this because, you know, in the U.S. we're like, don't show us equations, we can read those on a paper. You know, we want to see like all the cool things that you can do. That's typically our focus. So many times I would just fly through that, but I've noticed here it's like, here's all the equations. Here's all the equations. So I don't feel so bad about presenting some simple equations. All right, so here is the 9-cell assembly. Once we break this away, we see some internal forces. All right, they're on the right-hand side, as well as potentially some external forces, although for free wave propagation, we'll get rid of those. We have an assembled mass matrix, assembled stiffness matrix, and then any nonlinearities appear in this term. They need to be weak, because I'm going to do asymptotics on this. All right, so we're looking at a standard set. Now, we have gotten rid of the infinite by looking at this 9-cell assembly. We can store all the unit cells. You can see all 9 of them, in fact. We're really interested in the degrees of freedom held by this unit cell, but we have all the left, right, top, bottom neighbors included. And so here is our equation of motion, if you like, for those 9 cells. Now, of course, this repeats for every n1, n2 pair. So it's really an infinite set. You can't look at just the second derivative, let's say, of n1 comma n2, because it has all the neighbors, and they have all their neighbors, etc. All right, so we've gone into the frequency domain. We look at now a weakly nonlinear model. Essentially what we do, if you notice, the unit cell's mass matrix now just becomes an M, because I'm going to cut out that center unit cell. And that's why there's now only the degrees of freedom for the reference unit cell N1, N2 that appears here. Here's all our neighbor stiffness terms. Here's our nonlinear term for our neighbors, and then there's anything external. I'll deal with lumped masses, although we don't have to. For discrete systems, they're typically lumped. We have a small parameter. Our nonlinearities need to be small. We have some nonlinear interactions here, and then for free wave propagation, of course, there are no external forces. All right, now here's the heart of the asymptotics. What we do is we look for a zeroth order solution, and then we look to correct it at the next order up. This is classic Lindstedt-Poincare as applied to these difference equations. We look for a frequency that's of wave propagation plus a correction. Right, so omega 1, when I talk about that, that'll be a correction. And we only keep this out to the first order. We substitute into our equations, and here's what's key. This is now, of course, the linear system of equations, and we can apply Bloch's theorem to that. Remember I mentioned we want to get down to a single reference unit cell. Well, we do that with Bloch's theorem. Now we can get rid of all those cells at the zeroth order. Once we have the solution at the zeroth order, it appears here on the right-hand side, and of course this is just a linear kernel again. So essentially by doing this, we've reduced it down to just a single unit cell, which was what we want to do. We can highly discretize that. I mean, you could look at very complex cases. In fact, all the generalized continual work that's done here could be very interesting in this setting. Right, so we do nonlinear wave propagation in these generalized continua, second-order gradient. You know, this is above my head. I don't know too much about this. However, it would appear to me that it would fit very naturally into this formulation. Okay. All right, so zeroth order we solve for Bloch waves. Francesco actually asked me, where are the plane waves? Well, here's where the plane waves are. Here are the unit cell degrees of freedom. Of course, is a vector. So we have a wave mode, much like in modal analysis and vibrations. We have a wave mode. In fact, we'll have n of these. If we have n degrees of freedom, we get n dispersion curves, and we have n of these modes. This is our wave vector. Here is our position vector of that unit cell, and then we've already gotten rid of the temporal part, the frequency in the temporal part, by doing a non-dimensionalization with the frequency. So we're at tau. We're at a frequency of 1, essentially. Now that's the Bloch waveform. Comes from Felix Bloch in quantum mechanics and periodic potentials. When we look at the wave number, if we work with the reciprocal basis for this wave vector, if we put it in terms of B1, B2, then we use the orthogonality. Of course, this is in terms of A1, A2. And we see these two propagation constants corresponding to lattice vectors in the B1 and B2 direction. So we call those propagation constants. Here is the solution. All right. Here, once you have this assumed form, it's going to form an eigenvalue problem. You can find all the other solutions for all the other unit cells simply by moving it to the left and to the right and the top and the bottom by these propagation constants. So if you're one unit cell away, you're one propagation constant away. If you're p away, then you're p propagation constants away. Now we substitute this into the zeroth order equation. We know this is the solution to the linear problem. We have this expression. It leads to an eigenvalue problem. If we have n degrees of freedom here, of course we have n eigenvalues, and each of those eigenvalues is a dispersion curve. All right, and that's what we do. All right, now once we have a solution at zeroth order, here's the jth branch. all right, or the jth wave mode, if you like. We take that and we have to substitute it into the right-hand side and remove secular terms, because we know secular terms are going to occur. These are terms where the solution blows up, and of course we lose the asymptotic nature of the solution. So we substitute it in. We note that if this is a quadratic and cubic term, of course it's periodic with period 2 pi. So we can take the Fourier expansion of that, and we can isolate only the first harmonic. Now there's many, many harmonics, of course, because we've taken the Fourier expansion, but this is the first harmonic. It's at the correct spatial dependence and the correct temporal dependence to be secular, to force this essentially at a natural frequency. It would be unbounded waves propagating. And so we have to remove those terms. And this degree of freedom here on this correction to the dispersion, to the frequency, is what allows us to do that. So we take this now as the secular term. We do solvability, which means we look at the adjoint problem. We project onto the adjoint mode, which is the Hermitian of the jth wave vector mode. That gives us solvability. That gives us essentially a term to solve for omega 1, and here it is. All right, so here's our frequency correction for the jth mode as a function of amplitude. We have to compute the Fourier coefficient, but otherwise it's done. Okay. All right, so that's the whole procedure. Now here's what it looks like. This is the simplest setting. Here would be a cubic chain. So we have a mass and we have a linear and a cubic stiffness. Here's the form of that. Here is the shift with amplitude. If we're a hardening system, we shift the dispersion up. And if we're a softening system, we shift the dispersion down. And you can see the correction term for this particular lattice. Well, not very much a lattice, just a one-dimensional system. Okay, so how might that be used? Well, here's a diatomic system. That means we have M1, M2, M1, M2, M1, M2. Okay, it just keeps repeating. This, in fact, is the correct description of some crystalline structures. If you propagate in certain waves, you in certain directions, you have a whole plane of atoms that move. Okay, so simple as this sounds, it's actually salt. This describes propagation of waves in salt. So here we are. I'm going to tell you about one device that you can take advantage of this behavior. We have what's termed the acoustic branch, and we have an optical branch, and then we have a bandgap for this system. Now that's just the linear behavior. And if we change the amplitude of the wave, note what happens. Here are our original locations, and this is going to be softening, so you can see the dispersion curves drop. So as we increase amplitude, the dispersion curves drop, and that means we shifted the bandgap location. And now we can think about frequencies, two of them, in fact. All right, if you think about two frequencies that are close to these edges, one at 1.5 and one at 2.5, depending on your amplitude, if you increase it or decrease it, you can let one of these waves through. And here's much like how we operate. We do the analytical asymptotics, and then we numerically simulate to see if, in fact, this behavior is correct. Okay? So here's what happens when we simulate. We send in both of these waves. We put a high gain. That's why we say this is tunable. Here's our wave coming in. Here's our nonlinear diatomic chain. We can tune this. We can change the amplitude of the wave coming in. And in this case, for high gain, only the high amplitude wave gets through, and you see very little bit of the low amplitude. And then if we do this again at low amplitude, then we get the low frequency wave. You can see the 1.5 hertz wave made it through, and the 2.5 didn't. All right, so this is a device. It's a nonlinear frequency isolator that's acting on these two frequencies. You could do multiplexing and demultiplexing through a channel acoustically using a device such as this. Okay. All right, now it gets a little more interesting when we look at two-dimensional systems. This is the simplest two-dimensional system you can imagine. It's, again, monatomic, meaning there's only going to be one mass in the unit cell. Again, we're looking at stiffness, that's cubic and linear. And here, not only can we shift the dispersion curves, and that's what's being shown. In fact, now I'm moving through a little more rational of a unit cell. This is called the Brillouin zone. This is the repeatable part of the reciprocal space, and we move on with wave vectors that go from here to x up to m and then back down. And you can see, of course, as we change amplitude again, we shift the curves. Not only that, we shift the band gaps, and there's a little animation to show that. But also we can do interesting things with group velocity. So the group velocity, which is how energy propagates, we take the knob law operator. This is a gradient with respect to the wave number components. We take the frequency, we take its gradient essentially with this knob law operator. We're working with a corrected frequency. We can get amplitude-dependent group velocities. Here they are. Okay, so here's our amplitude dependence in that correction term. And interesting things can happen. Now, what I'm going to show you is for a diatomic system, two different masses, M1, M2, repeating throughout the lattice. We look at these isofrequency contours. Here's one at 1.75 radians per second. Normal to this would be your group velocity. All right. So as this changes with with wave number, you can calculate the normal direction and get the group velocity. Here it is. If we happen to have a circle, the group velocity would be a circle. Here, because we get this shape that has a little anisotropy to it, we get something that looks a little more complex. All right. So bear with me a little bit. As we increase the amplitude, something interesting happens. All right. So as I keep hitting X, enter, I'm going to increase amplitude a little bit and a little bit. You can see the amplitude increasing here. I'm increasing it more. Notice that this group velocity contours are starting to come in, and it forms what's termed a caustic eventually. It's pinching in and then boom, okay? Now we do not have a wave that can propagate with simply an X component of group velocity. We don't have any dispersion on this line. We have to jump up to Y. That means the lattice won't support, at this amplitude, waves that are going to propagate strictly in the X. And that's what our perturbation approaches are telling us. So again, we can go and simulate. As I said, we try to learn from the perturbation approaches. I think, am I running out of time? Okay, I think I can go quickly. I'll just show maybe just some results. We can do this numerically. Of course, we can inject any type of plane wave we like. We numerically validate this stuff, by the way. This is showing two branches, and the numerical simulations with 2D FFTs are shown on top of the analytical. That's not really what I want to show you. Okay, here's what I'd like to show you. Now let me go back to that lattice, and we'll inject a small amplitude wave, and we'll inject a high amplitude wave. So here's our low. It's going to, it didn't go. Try that again. The low, I'll start with the high. Notice there's no group velocity. There's no energy propagating to the X as we predicted. And then at low amplitude, essentially, you can see it's almost isotropic. All right. So let me see. I'll start that one more time. So here's low amplitude. Here's high amplitude. You can see the behavior we're predicting asymptotically is correct. And so again, you can do filtering. If you want some information to come through, you could put a gain on it, or the opposite. In fact, you could do low amplitude and put your sensor here, your receiver here. If you put your receiver here, you won't get any of the high amplitude. You can saturate signals this way. All right, this was kind of interesting. Here we're taking, this is two nonlinear materials that is linearly equivalent to this inner material. And so at low amplitude, this is going to look like a homogeneous slab. And at high amplitudes, we're going to start to see differences. So here's low amplitude excitation is a very directional lattice. You tend to propagate in the 45s. Here's high amplitude. You can see that this material is now opening a waveguide, and we call this a nonlinearly activated waveguide. All right. Again, just things you can do. I mean, these are small perturbations, but you can get very different behavior out of these systems, very drastically different behavior out of these systems. I won't cover this. Wave-wave interactions allow us to do even more. In fact, it allows us to do things like refocus with a control wave. So this is a correction to the group velocity at this next order up. Allows us to do some refocusing. For example, if we're originally focusing here, we can put a gain on the signal and focus down below if we like, using a control wave that's coming to the right and the left, a very small control wave, in fact. We've now done one experiment. I think I'll close on this. We've done one experiment really relating the classic Duffing oscillator, which would be here. Here's its frequency response. This is the backbone curve. Two dispersion curves. Now, I've been showing you pictures that are just simply this front face. Here's your wave number. Here's frequency. But as you change amplitude, you get a whole family of dispersion curves. And we can measure these in a simple periodic string, and we've gone and done that, in fact. This is 250 microns, so it's a very small drill that goes through some lead balls. We plot the frequencies. We really kind of follow. Well, let me show you one thing for fun. Here's a wave above the cutoff being excited. Now, you'll watch a small wave bounce back. That's because you put a step function in it, and it'll eventually die. But here's the real function you're putting into it. And notice the chain doesn't respond at all because the wave can't propagate. It's in the bandgap. Here would be wave propagation along the dispersion curve, so it's not in a bandgap. You can see right away the wave propagates. And in fact, near the edge of the brilliant zone here, we know the masses should oscillate up, down. They should be 180 out of phase, which you see. All right, so we do some work to experimentally measure this, and here's the final result that I'll discuss. Here is a theoretical prediction of what a backbone curve should look like, and here's ours from the wave propagation. Admittedly, a little bit of a mismatch, but actually the correct trend is there. All right. All right, let me conclude. So I presented this perturbation of work yields closed form expressions. We see all this amplitude dependence, and we're trying to exploit it. I didn't talk so much about wave-wave interactions. Follow-on work, we'd like to do more sophisticated experiments, actual wave-type experiments. I think that needs to be done. We need to start constructing devices. I think there's plenty of opportunity to do that. I think we've shown interesting results. And then we want to start looking at strongly nonlinear periodic materials and structures. Maybe that's an opportunity for some collaboration with people here. And that's it. Here's just a number of papers that have come out of the work. Thank you.
Some questions? You have a slide. It's nonlinear spring model. You didn't show.
You mean a physical nonlinear spring? There's many ways we can get nonlinear springs. We can get them from clamp beams. We can get them from producing a spring that's a composite, which is essentially a linkage that's giving us nonlinearities. And then maybe more promising, we can do it with shunted circuits. So we can do it with circuits as well. But, plenty of MEMS devices. In fact, the MEMS crowds design around the nonlinearities. So nonlinearities in the MEMS world is very, very common. It's not hard to achieve.
Have you employed some geometry in which you can see bandgaps in linear material?
Yeah, actually, the diatomic systems, if you notice, the bandgap has to be there in the linear case, although actually we can get purely nonlinear bandgaps. But the bandgap already has to be there. We're just shifting it with nonlinearities.
So it's possible to have a bandgap in linear?
Oh, yeah, absolutely. In fact, 99.9% of the work you're going to see on bandgaps is linear systems.
If you observe localized wave,
the answer is no, because we don't look at it. So the question is, do we see any localized waves because we see zero group velocity? The answer is no. We haven't found any breather-like solutions, as they're called, but that's really because we don't look for them. But they're there. I'm positive they're there. It's just not something we look for.
Do you plan to build some two-dimensional systems?
Yes.
Which size?
Well, for us, these can get very small. These can be NEMs. These can be MEMS or NEMs, but for me and my expertise, I don't go into the clean room, so we'll build macro-scale models of them.
Okay.
But we work with Sandia National Labs, and they're synthesizing at very small scales these devices. We've just begun that collaboration, but it's not my interest so much.
But in this system, if you have so many vibrations, they accept some fatigue or they break or this system?
Sure, yeah, like after millions of cycles.
Yeah.
Just like, literally, your cell phone has this device in it. It has a surface acoustic wave, so it lasts the life of the device.
Thank you very much again.